We'll start with the prayer.
शांति शांति। ॐ असतो मा सद्गमय तमसो मा ज्योतिर्गमय मृत्योर्मा अमृतं गमय। ॐ शांति शांति शान्तिः। ॐ सर्वेषां स्वस्तिर्भवतु, सर्वेषां शान्तिर्भवतु, सर्वेषां पूर्णं भवतु, सर्वेषां मङ्गलं भवतु। ॐ शान्ति शान्ति शान्तिः। ॐ लोकाः समस्ताः सुखिनो भवन्तु, लोकाः समस्ताः सुखिनो भवन्तु, लोकाः समस्ताः सुखिनो भवन्तु। ॐ शान्ति शान्ति शान्तिः। ॐ पूर्णमद पूर्णमिदं पूर्णात् पूर्णमुदच्यते पूर्णस्य पूर्णमादाय पूर्णमेवावशिष्यते। ॐ शान्ति शान्ति शान्तिः। ॐ श्रीगुरुभ्यो नमः। हरि ओम्।
So, good morning. Please pray to your parents for a minute. I'll wait. Thank you. Who should give the next presentation? Sandita? Which group?
So group 7.
Group 7, na? Okay. So who's giving the
Sir,
presentation?
Lakshmi Sivakumar, roll number 23.
23. Okay. Okay. Continue, please. Yokumar.
Yes. Is the screen visible, sir?
Yes, visible.
Good morning, sir. Good morning, everyone. I am Lakshmi Sivakumar from Group 7. I am here to give a presentation on wig design for our specified business jet. And these are our mission specifications. This is the mission profile for our business jet. And by finding the CL of the aircraft required from the start of the cruise to the end of the cruise, we have chosen a supercritical airfoil, which has the given characteristics and which also have a CL inside the drag bucket. From the experimental data, we have information like critical Mach number and drag race Mach number. Coming to the planform area, which we find from the wing loading and the weight of the aircraft.
Sivakumar, can you show the earlier slide? Earlier one, yeah. So which one of these graph did you take?
Sir,
What are those symbols? What do those symbols mean?
Sir, for different Mach numbers, sir.
Mach numbers, okay. So you took for which Mach number?
Sir, our cruise is about 0.79 Mach, sir.
Okay.
And we can observe the critical Mach number at 0.725. After Mach 0.725, we have a high increase in drag. So accordingly, we would give the sweep.
That is okay, but which curve did you choose? The last one, huh? For your thing. So
Sir,
many curves are given. Which one did you choose? Only the
it
last.
is in the no, sir. This is in the triangle shape, sir. Actually, it is very hard to see. But this data
So what
I
you use?
have taken from airfoil tools.
No. You take only from here, but choose only that curve and display. Don't display for everything here. Manually, you can plot and show.
This data is not given, sir, separately.
You have to take the points and plot it. What are you doing for your report? You have to do something, no?
Yes, sir.
It's not just cut and paste. So to be clear, if you are presenting to a outsider, you should know what you are doing. You shouldn't know. He shouldn't have to figure out what you have done. You should be very clear.
Yes, sir.
So you draw only that graph, nothing else. CM is not required for your thing. Don't draw it. Draw on, take the points. You can draw on several graphs, graphical editors, or draw on a graph sheet and take a photo.
Okay, sir. Okay, sir.
Mainly CL versus alpha, and the second one, CL versus CD. That is only very important for me. The CM you can use later. Right now, I'm not too keen about the CM.
Yes, sir. These are also the data, but these are for particular Reynolds number.
Don't use these airfoil tools or Xfoil. Okay.
Okay, sir.
If you have experimental results, just stick with that.
Okay, sir.
Take only that and use it. Okay, that is more accurate.
Yes, sir.
For this purpose. Yeah, go ahead.
These are at 10 power 7, sir, Reynolds number. We got the plan.
For high Mach number, usually it is a high Reynolds number. But nowadays, with MAVs, you have a peculiar situation where you have high Mach number coupled with low Reynolds number, which is not investigated properly yet. Okay, so it's high Mach number you take it for granted that's high Reynolds number for normal planes.
Okay, sir.
Yeah, continue.
I found the planiform area, sir.
Hmm.
From the aspect ratio from the reference aircrafts, we have chosen to be 12.
Wait, one more point I want to see. Go to the earlier graphs. You can see that the curves vary a little bit for various Mach numbers, correct?
Yes, sir.
Actually, for lower Mach numbers, for lower Reynolds numbers, the variation is even more severe in general.
Okay, sir.
Okay. That's why we don't bother so much if it's high Reynolds number. Still there is a variation, but we say that, okay, it's acceptable. Yeah. Go ahead, please.
We have from the chosen aspect ratio, we can found the span of the wings.
A
And
very high aspect ratio for transonic Reynolds number. It's too high for transonic Reynolds number. So choose aspect ratio from 6 to 8. What does it comparison aircraft have aspect ratio?
12, sir. 12 point something. 12 point.
Ah,
Bombardier, sir.
okay. 12.
Yes, sir. 12 to 13, I guess.
Oh, just check out. Huh?
Okay, sir.
Check whether it should be half that value means I'll be happy, but this seems to be very high. Anyway, check out and let me know. What is the
I have
span? B is
yes, sir.
semi-span
It is
or full span?
full span, sir. I am getting in the same range, sir, of that Bombardier.
Where did we get S from this?
Sir, as we found out from wing loading from the previous,
Mm-hmm.
we have found the region of the
Okay, go ahead.
WYS.
Yeah, go ahead.
From the experimental data, we have found the sweep, sir.
Hmm.
We got at 35.45 degrees, which should be the maximum sweep. After that, performance will be decreased.
Hmm.
We have chosen the taper ratio, sir. From,
Okay. Yeah, go ahead next.
and from the formula, we have found the DCL by D alpha for the wing.
What is the unit for DCL by D alpha? Per radian.
Radian.
Per radian.
Yes, sir, per radian. And actually, I varied the aspect ratio, sir, but we are getting similar, like not much of variation.
Okay. The effect
And
of Mach number is more there then. Okay.
yes, sir. And from the airfoil data, we have found the alpha 0L, and from that we have found the CL, means we can draw the
Again,
CL.
you can find it. This is for 3D. Yeah.
Yes, sir. The curve is for it is for 3D, sir.
3D you can find it using the formula, right?
So yes, sir. But we need alpha 0L, no, sir.
Mm-hmm.
Yeah.
Alpha 0L for the 2D. What do you have?
Yes, sir. That is a minus 4.75, sir.
Take the same thing.
Yes, sir. I did with it only.
So why do you need this graph? We can take it from the experimental value, no?
Yes, sir.
Yeah, take it from experimental value.
Coming to the planform geometry, these are we found from the calculation, sir.
Okay.
Root chord as 3.816 meters, tip chord as 1.526 meters, and the mean end chord is 2.834 meters.
Okay, good.
And we have found the sweep angle at C by 4 quarter chord. It is 34.400 meters.
Okay, next.
Coming to the wing drag estimation, as we choose the CL to be in the drag bucket, as a chosen CL is in drag bucket, it would be reduced to this.
Right. Next.
Yes, sir. From the formula, we can found the F, sir. I got 1.5767.
Okay. Next.
And as we have having low wing, Q is taken as 1, sir.
Oh,
and
yes.
I have found the Reynolds number.
Next. CF you have found. CD naught is 0.00895. Okay.
Yes, sir. The
Yes,
comparison.
wet bias. Okay, right. Good. Okay, next.
These are
Good.
the two.
Where is the total drag? You have to find at cruise what is CD naught plus KCL squared into half rho V squared S. That will give you total drag on wing
Okay, sir. At some angle of attack.
at some CL, the cruise CL.
Okay, sir.
Correct? You have the
Yes,
cruise
sir. Yes.
CL. Yeah,
Yes, sir.
using the CL you can find. Don't find angle of attack right now. You can do it later, angle of attack. Now, where are the curves comparing with 2D? CL versus alpha.
Sir, CL versus alpha.
You have shown two curves here, CD versus CL. What are those? Right hand side is
Right hand
2D and
side
left
is
hand side is 3D.
yes, sir.
Similarly, compare CL versus alpha also.
Okay, sir.
And then show me the geometry of your wing. Drawing.
Yes, sir.
Okay, these are missing.
Okay, sir. I
Okay,
will add
good.
it, sir.
Okay, now for questions to Shivakumar. Any questions to Shivakumar?
Sir, I have a doubt, sir.
Who is it?
Myself, sir.
Myself is name. Yeah. Tell me.
Sir, here we are inducing sweep now, sir, to
Yeah,
decrease the Mach number at the airfoil.
critical Mach number. Yeah. Normal Mach number. Yeah.
But effective Mach number will be changed now, sir, near the wing.
That is why this beta is there for.
Then the lift produced will be changing now, sir.
No. For the lift produced, you use the actual V infinity. Your wing
Okay.
area will automatically become less.
Oh, okay, sir.
The effective wing area. Okay.
Okay, sir.
You don't have to worry about it. You find the velocity, free stream velocity. Okay. Or that is the easy way to do. Otherwise, you have a formula with for lift using the Mach number also. Instead of half rho V squared, you use gamma P m squared, half gamma P m squared. But then what is P infinity? You have to find in that case.
Okay.
If it is not there, convert this to velocity and find half rho V squared.
Okay.
For finding drag, I am telling.
Yes, sir.
Okay. Okay, thank you.
Thank you.
Thank you, Shivakumar. We'll move to the next group. Next group 10, right?
Yes, sir.
Rita had sent me the order. Thanks, Anita. Whose roll number is?
56, sir.
56. Name?
Yarini.
Yardini. Okay. You can proceed, Yardini.
Yes, sir. Sir, is my screen visible, sir?
Yeah.
Okay. Good morning, everyone. I'll be presenting the wing design presentation on behalf of my team. Our aircraft is interceptors. So these are our mission requirements, and these are the values we got from the previous presentations.
Yeah, proceed.
Airfoil shape selection, we found the Q value and cruise at start of the cruise and the
This wait. When you use this Q value, okay, don't find it in kg per meter per second square. The
Okay,
unit
sir.
should be Newton per meter per second square. Only then you'll get the correct value.
Okay, sir. Okay, sir.
Use the Newton one, so everything will change. CL will change. Newton means multiplied by 9.81. So CL will be further less.
Yes, sir.
Okay.
Yes, sir.
Most important, everywhere, when you evaluate Q, it should be Newton per meter per second squared.
Okay,
Only
sir.
then the W and this will actually, Oh, W are using kg, is it? W by
Yes.
S in kg per meter square.
Yes, sir.
Ah, okay. In that case, you are right. Okay. But if you usually you take W in Newton, because when you say T by W, there you'll make a mistake if you take W in kg.
Okay, sir.
But T by W, what do you do? Thrust is in newtons.
Yes.
So W should also be in newtons for it to be non-dimensional. So
Okay, sir.
everywhere you use weight in newtons. That is why you should use Q in newtons. But here, if you use WAS as kg per meter squared, then this is okay.
Yes, sir. So we got the CL value at the start of the quiz and end of the quiz as 0.1.
Okay. Right.
So these are the graphs we had.
What is the airfoil?
NACA 0006, sir.
That is the most important thing you should say.
Okay.
Without that, we don't know what you are talking about. The airfoil shape you should show.
Okay, sir.
Show the airfoil shape. Okay, yeah, next. And show only the curve which you are using. Yeah, this is okay. This is okay. You
Yes,
show it before that. Okay. Show it
we
before that
compare
curve.
both
Compare what?
TSAGI 12 and NACA 006, sir.
It's not nowhere in the graph you are mentioning that. There should be a label in the graph.
Okay, sir.
Which one corresponds to which, we don't know.
Okay, sir.
See, when you see a report or presentation, you won't be there to explain.
Yes, sir.
The report should speak for itself. That is why.
Okay.
Okay. Yeah. Continue.
This is the airfoil we got.
Okay. What's your Mach number?
1.6, sir.
Wow. Okay, good. Okay. Good choice. Yeah, go.
Yes, sir. Aspect ratio we found using the
Yes, fine,
formula.
fine. Next one.
Taper ratio also we got 0.2.
What is the wing area you got?
Wing area is 1 minute, sir.
There are some change in your weight estimation. Okay.
Yes, sir.
So make sure everything else changes. The wing loading should not change because of that. This calculation may change because of that.
Okay, sir.
I sent to someone. Is it to Niveta?
Yes, sir, but the wing only during the loiter and combat, sir. This is before during cruise, so it wouldn't change.
No. What I am telling is your total weight may change because of that. You put it in the iteration. Okay. When you take
Yes,
the
sir.
total
I
weight.
checked the values remain same, sir. Only the calculation had to be more elaborate.
Remain same means then it will doesn't affect the wing area. How? If you make a change, it doesn't affect that doesn't affect means it will affect in some way, no? How much does it affect?
No, sir. The calculations which we did weren't wrong. As in, it just had to be explained more elaborately.
I see. You send me because I haven't really marked you yet because of that. You send me the changes.
Okay, sir.
Okay, yeah. Okay. Go ahead.
Using all these formulas, we found the sweep angle at the chord, sir.
Okay.
And
next.
the maximum thickness to chord ratio. Then these are the values we got.
CR, CT, CMAC. How did you find CMAC?
Using the formula, sir.
Which formula?
Sir, this one.
Okay, yeah. You know how to find it diagrammatically?
No, sir.
Okay, yeah, go to the next one.
This is our planiform view. We found all these values like sweep angle and root chord.
Fantastic. Good. Go to the next one.
This is our 3D wing design, sir.
3D is not necessary at this point of time. Okay. Later, when you integrate with fuselage and all, it will be nice to have.
Okay, sir.
Okay. Right now, the platform view is good enough.
Okay, sir. We found the 3D lift coefficient and dCl by d alpha is equal to that 2.52 per degree C
Huh?
per radian.
Uh-huh.
Should be.
Seems to be too high. Something is wrong here. If you use this, you'll get per radian. Okay?
Yes.
You have to
Yes,
change it per degree.
okay.
See, 2 pi is how much?
So we
Roughly.
took the
Pi is how much?
tangent value.
No, I'm asking the value. What is the value of pi? 3.14.
1.4.
2 pi will be?
7 point.
No, 6.28.
Yes, sir.
So 6.28 approximately per radian will be your theoretical value for 2D.
Yes, sir.
So 3D will be less than that only.
Okay.
If it's 2.52 per degree, no, you will be creating history.
Okay.
Okay, so you have to say per radian or convert it to degree. It will be some 0.005 or something like that.
Okay, sir.
0.05 or something, 0.03, somewhere there. Okay. Yeah, go ahead.
We found the wind drag estimation. So by using these formulas, we got
Okay.
these values. And we need to find
what
CL.
is the total wing drag in Newton? You need to find out.
Yes, sir.
You found CD, right?
Yes, sir.
And here that in the formula also you put 1.3 star CL squared is missing. Only CL you have put.
Okay.
0.008 for last line.
Yes, sir.
0.0084 plus 1.353. What is 1.353? K is so high here. Okay. Star CL squared. Just check your value of K. How did you find K?
With this formula.
Formula, it doesn't give you the correct K. K should not be 1.353.
Okay.
1 by pi into
Sir,
aspect
excuse me,
ratio is
sir.
2. Huh?
Sir, this is Bonde, sir, from same group. Sir,
No,
that is
don't.
0.13.
0.13. That
Yes.
looks reasonable. And CL squared, not CL.
Okay.
Okay, so recalculate CD.
Okay,
Once you
sir.
calculate CD, find half rho V squared S into CD. That will be drag. Okay? Okay, good. Any questions to Yaini? See, show me the earlier slide.
This one, sir.
There won't be any shift in CL at 0. Take it as a 2D.
Okay, sir.
Okay.
Sir, then no need to find CLS.
What? No. See what she has done. CL at 0 lift. Not alpha is equal to 0.
Okay.
Alpha when CL is equal to 0 will not change. So you can find this actually. If you want.
Okay, sir.
Alpha at CL is equal to 0 will not change from 2D. The 0 lift angle of attack. Okay?
Okay, sir.
But this you can find out. If you know that alpha at CL is equal to 0, you put CL at alpha is equal to 0, which is not really necessary. You have to put alpha at CL is equal to 0. 0 lift angle of attack. That will be the same as 2D. That is the only thing which will be same as 2D.
Okay, sir.
Okay.
Okay.
So you plot these. This plotting you have to do. Okay.
Okay.
So any questions to Yarini? Okay. Thank you, Yarini.
Thank you, sir.
Next is group 1. Who's presenting in group 1?
Sir, Swaroop, 46.
Group 46. Okay. Yes, Swaroop, go ahead.
So these are the requirements we took, sir, for wing design.
Just hold on. Service ceiling, range, payload, 80 kg. Your type of aircraft is?
Sir, piston prop.
Trainer, piston prop trainer.
Okay.
Is it?
Yes, sir.
Okay. Yeah. Okay. Good.
So this is the mission profile. And for wing platform area, we got it as 13.8 meter square.
Very good. Next one.
For airfoil selection, for the comparison.
Right. Go to the next type. Good. You took these three. Next. By all 5 series, sir? Or 5 digit? All 5 digit?
Yes, sir, 5 digit.
Any reason?
Uh,
What is the thickness of these airfoils?
Sir, from 15 to 12.
Great. Okay. Yeah. Go ahead. Next one. 18 is there? That is 18, 18%. Second one. Green one is 18% thick.
So green is 18, sir.
Okay, yeah. Go ahead, please.
So these are the graphs related to those three.
How did you get these graphs?
Sir, we plotted this in XFLR.
XFLR. Okay, but you can't plot this in XFLR. You should have got it from somewhere else. After stall, the XFLR doesn't work properly.
Okay. And we will notice that 23012 will have minimum CD, sir.
That is obvious because less thickness. Okay. But you still have, because it was a low one, you go for a higher thickness, up to 15% you can go actually.
Okay.
Because later on, in structural point of view, you will get benefit.
Okay, sir.
The weight will reduce. So you can actually choose the 15% or 14% is best. 15 is okay.
Okay.
Don't go for 18. That will be overkill. Then you lose so much in aerodynamics. You can actually sacrifice a little bit of the aerodynamics for benefit in structures. Actual weight. That will actually, save your weight and so decrease the drag in that way.
Yes.
Okay.
So then we chose.
This is not applicable for high-speed designs. For your low-speed designs, you have this special, this one. Okay? Special criteria that around 13 to 14% thickness will be the optimum. You will find it in the book also when you read somewhere.
Okay.
So 15% is close to 14%. That will be actually a better option than 12. Not that I'm telling you are wrong. Okay.
Yes, sir.
I'm not telling you are totally wrong or something like that, but it will be better if you take the 15%. Anyway, go ahead. Yeah.
Okay. Then for taper ratio, which was it a 0.4 and a 0 degree sweep angle.
This 0.4 is from comparison aircraft, is it?
Sir?
The 0.4 taper ratio you took from comparison aircraft?
Yes, sir. 23012.
Hmm?
The 23012, sir, like that one shows.
No, that is the airfoil.
Yes, sir.
Taper ratio is not related to airfoil, it's related to the wing, no? What is taper ratio?
Sir, CT by CR.
What is CT? What is CR?
Sir, tip and roots are called.
Okay. So that ratio, how did you get as 0.4? On what basis did you choose its 0.4? Because it's close to elliptic distribution, or
Sir?
because it is closer to elliptic you took, or because it is from comparison aircraft, on what basis did you choose? I'm giving you all the answers. Now, you're so used to multiple choice. You have to tick the right one, that's it. Where did you choose? You mentioned this reason in your report. Find out and mention the reason, okay?
Okay.
Y lambda 0.4 you took. I'm not telling it's wrong. You shouldn't write Y.
Okay. Then we got a relation between CL and alpha. Then for planform geometric relations.
CL and alpha means, you mean 3D CL and alpha?
Yes, sir, 3D CL.
This 4.79 is, there's no unit there. What is that? What is the unit?
Sir, K. Oh,
Then if you have the graph,
unit,
see,
it's
6 GCL by D alpha you're taking is 6.28, no?
sir, unit for 4.79 is rad power minus 1.
Okay, even for 6.28 it's the same, no?
Yes,
Stop.
sir.
Now what I am telling is, where did you take this 2 pi? You have the graphs with you, no? You have the graph CL alpha. Go back to the graph. What is the first graph? Top graph, left top, CL versus alpha.
Yes, sir.
Can you measure from this and take that value instead of 2 pi? Take 2 points, take the slope.
Okay, sir. But in textbook, it was given CL by DCL.
Yeah. But I am telling, instead of 2 pi, you substitute this in the formula.
Okay.
The value you get from here. That was based on, see, in textbook, he can't put for all airfoils, right?
Okay, sir.
So he has generally put assumed in airfoil theory, it's 2 pi. That is the maximum possible. There's a thick airfoil, there may be, slight deviations. Maybe less than 6.28, maybe only 6, we don't know. Measure from the graph. In the linear portion of the graph, you measure.
It was 6.6 something.
6.6 is too high, it won't be. It cannot be more than 6.28.
We'll check once, sir.
See, you will get it in degrees. The graph will be in degrees. You have to convert it to radians and compare.
Okay.
Yeah.
So then for wingspan, we got 9.1 meter.
Okay.
And this we designed in X.
Yeah, now show me the problem here is, where is your leading edge?
So the zero sweep angle, though. Right side.
Okay.
Yes, ours.
Okay. So you show a plan form area, that's good enough. We'll get a better. This is good enough. You're shown the. You also show the airfoil cross section which you chose.
Okay.
You chose 3 of them. Showed 3 of them. Just show the one which you chose in this figure by the side in a small figure.
Side section, sir.
Yeah.
Okay.
Okay, good.
Then using
Yes.
this.
Yeah. Next one.
We got relation between CD and CL square.
Now at cruise CL, what is the CD you calculate and calculate the drag in newtons. CD you have.
Yes,
What is the cruise CL you took for the aircraft? How did you design your airfoil? How did you choose your airfoil? Go back. Where is CL cruise for airfoil? How did you find out?
the CL cruise we got it from previous presentation.
Using the CL cruise only, you estimate that CD. That's how you should choose your airfoil also. Airfoil selection itself, the CL cruise will play a part. No, what part does it play? You have minimum drag at CL cruise, right?
Yes, sir.
Does the airfoil satisfy that condition? You haven't checked. You haven't shown. You have to check that.
Okay, sir. Okay.
So now this CD and that CL cruise, you will get one CD, correct? You put substitute that value of CL cruise.
Okay, sir.
For that CD, you find drag, which is half rho v squared S into CD.
Yes, sir.
So find it in Newton. Because when you go to the engine, engine selection, you should know how much thrust your engine should have, correct?
Yes, sir.
The thrust should be more than the total drag of the aircraft. Correct.
Yes, sir.
Now this drag at cruise, drag means take the cruise density, okay? Cruise at that high density will be different.
Yes, sir.
Half rho v squared. Use that rho at cruise. Now the thrust should be more than this at least. So for that you had the wing drag, fuselage drag, tail drag, and then the engine drag also. And say engine should produce more thrust than the total of all this drag. That is why you are calculating the wing drag here.
Okay, sir.
Now if you get CD, you don't know anything. If you get the drag in Newton, you will know something. Okay?
Okay, sir.
Okay. Thank you, Sarup. Any questions to Sarup?
Sir, just the graph, sir.
Yeah.
Only.
Show me the earlier one. Yeah, from here it looks better. It looks better that you chose the bottommost one, correct?
So that is 2D.
12%. That's what you did, correct?
Yes, sir.
What I am telling is it is better to the middle one. Although aerodynamically it is not efficient, I agree. Okay?
Yes, middle one is for the whole wing.
No. Middle one is for you check. Why do you give the 3 if it is for the whole wing? What is the top one then?
So that is 3D lift coefficient.
What is the difference between 3D and wing? Something wrong then here.
Sir, I had the same doubts.
You have committed a mistake. You have to take only one airfoil which you have chosen. Compare that with your wing. That's all.
Okay, sir.
Okay.
I'll check what's the mistake.
If you have doubt, you can ask me or discuss with teammates. Okay.
Okay, sir.
You can call me anytime. You can mail me. You can on Teams. You can send me a message. You can WhatsApp me.
Yes, sir.
Okay. So many avenues are there. Don't feel shy. Just call me.
Yes, sir.
Okay. Yeah.
Thank you, sir.
Welcome. Any questions, Swaroop? Otherwise, we'll close for the day. As you can see, I need more and more. If I see that you haven't understood, I spend more time with you. So please, try to be up to date. You'll be wasting your own time. The knowledge you'll be gaining in this depends on how much all of you work together. If you go slow, it is bad for your own future. Okay. Swaroop, don't delay in asking doubts. Many people are like Swaroop. Wait till the last moment, then you realize you don't know something, then you go scramble and find something. Don't do that. Do everything beforehand, better. So, okay then. You can stop the recording.